Okay, so now we will proceed to the advanced part. That's the most awaited part of this video, which is the Thevenin's and the Norton's theorem. Okay, so you can see on the screen it says the Thevenin's theorem, and next you will see the Norton's theorem. So what does the Thevenin's theorem say? Okay, before getting into discussion about Thevenin's and Norton's theorem, I would like to say, what's the significance of these theorems? Like why we are learning these theorems? The only reason is that when we have very complex circuits, okay, very complex, like lot of resistors, like you see here, the circuit given there, that's pretty much complex. But there will be even more complex circuits that are very like complex, that you can't solve them directly using the Ohm's law, the Kirchhoff's law, and the potential divider circuit law. Okay, so the most important significance of Thevenin's and the Norton's theorem is that you can apply these theorems to solve any complex circuits. Okay, and another thing, before making or building a circuit, you have to do calculations, like which component will get how much current, or how much voltage will be provided to that connected component, right? So before you do it in real, like before building the circuit on the breadboard or in the breadboard, we do actually calculate the voltage and the current that will be provided to the load. Okay, so Thevenin's theorem and the Norton's theorem are the most effective way to figure out how much voltage will be across that load, okay, and how much current our connected component, that is our connected load component, will get from the circuit. Okay, this is the significance of Thevenin's and the Norton's theorem. Okay, now let's get started with the Thevenin's theorem first, and then we will move on to the Norton's theorem. Okay, so the Thevenin's theorem says any network that has two output terminals A and B can be replaced by a constant voltage source with EMF E in series with an internal resistance R. Okay, so you see on the left side there's a complex circuit, okay, and this is basically the load resistor. Okay, and if you see on the right hand side the circuit, it's very much simple circuit, right? So the theorem says if your circuit is like this, okay, then you can replace the load resistor into a much simpler circuit like this, where the load will be connected in series with an internal resistance R. You see there an internal resistance R and an EMF source E. Okay, now the question is, what is that internal resistance? Where does it come from? And what's the E here, the EMF source? Is it the EMF source the same as that EMF source? The answer is no. That EMF source E is not similar to the EMF source here, 6 volt. It's not similar. Okay, this EMF source is basically called as the Thevenin's voltage source. Okay, it's called the Thevenin's voltage. This is Thevenin's voltage. Okay, this is the Thevenin's voltage. And what's the R? The R is basically it's named as internal resistance in the theorem, but actually it's not like the internal resistance of an EMF source. Okay, it's basically it's called as the Thevenin's equivalent resistance. Okay, it is termed as internal resistance here, but it's not actually the internal resistance of an EMF source. Okay, so the small r you can see, which is termed as internal resistance here, Okay, it is Thevenin's equivalent resistance. Okay. Okay, now how can we get them, Thevenin's voltage and the Thevenin's equivalent resistance? Okay, how can we get them? So basically, if you see the next part of the theorem, you can get some idea about how can we get the E, the Thevenin's voltage, and the Thevenin's equivalent resistance. So the next part says the value of E is the open circuit voltage between A and B, and R is the resistance of the network measured between A and B with the load disconnected and all sources of EMF replaced by their internal resistance. So the next part is saying, if we disconnect this part, okay, if we disconnect this part of the circuit, that means if the load resistor is disconnected, then we will have the only A-B terminal, right? There's no load. Okay, so Thevenin's voltage will be the PD across the terminal. The PD across this terminal will be the Thevenin's voltage. Okay, now the question is, I'm using the word Thevenin's voltage repeatedly, but what exactly Thevenin's voltage mean? Like, if I define Thevenin's voltage, what does it mean? So you can say simply, Thevenin's voltage is basically the voltage that would be supplied to the resistor, the load resistor. Okay, like when the load resistor will be connected here, then how much voltage the load resistor, like how much voltage would be across the load resistor, it's basically the Thevenin's voltage. Okay, so using the Thevenin's voltage, you can understand like how much voltage will be supplied to the load resistor as we connect our resistor there, or our component there. Okay, so now the question is, how does it work? Previously I have showed you the potential divider circuit equation, right? So just think here, the voltage output was across the resistor R2. Look, as when I explained this circuit, the potential divider circuit equation, I told you that when we will discuss the Thevenin's theorem, we will need idea from the potential divider circuit. Okay, so if we look on this resistor R2, across this resistor R2 we got the output voltage, right? So whatever resistor you connect across the resistor R2, let's say we put R3, another resistor we put there R4. Okay, as much as resistors you put there, all resistor will have the same V out, right? Similarly, if you see in this Thevenin's circuit, when you calculate this E, okay, the Thevenin's voltage, this voltage will be across the load resistors. Okay, like this will from that, it will be not exactly the voltage across the load resistor. It will tell you like how much voltage will be available for the load resistor. There's a misconception, like it will not tell you exactly how much PD will be across the load resistor. Thevenin's voltage is not the PD across the load resistor. Okay, it will tell you how much voltage will be available for the load resistor to take. Okay, so if you define Thevenin's voltage, the Thevenin's voltage is the voltage when the load resistor is disconnected from the terminal of the original circuit, and the Thevenin's voltage is basically the voltage across the terminal. So here the terminal is AB, because from that part we took out the load resistor, right? As we took out the load resistor, there's no resistors there, so the circuit is discontinued between part AB, and the voltage across the terminal AB will be the Thevenin's voltage. Okay, so Thevenin's voltage is what it will tell you. It will tell you how much voltage is available for the load resistor to use. Okay, that's the Thevenin's voltage. And Thevenin's equivalent resistance. So Thevenin's equivalent resistance is the total resistance. The total resistance, that is the equivalent resistance of all other resistors except the load resistor. Okay, so after the load resistor has been taken out, let me draw the circuit again. Okay, just at the bottom. Okay, so this is a fixed resistor, that's another fixed resistor, then there's another fixed resistor here, another fixed resistor. I'm not writing the magnitude. Okay, I'll just show you the diagram and explain from there. So now the circuit is like this. The load resistor has been taken out, so the PD across the terminal AB will give you the what you say, the Thevenin's voltage. Okay, so the Thevenin's resistance. What's the Thevenin's resistance here? So Thevenin's resistance is basically the resistance of this circuit, because here the load resistor is not present. So after the load resistor has been taken out, the existing circuit has this many resistors. So the equivalent resistance of all of these resistors will be the Thevenin's equivalent resistance. Okay, so when you have a circuit, a complex circuit, there will be a load resistor will be given. The scenario is like this: a complex circuit will be given and the load resistor will be marked out. Okay, and then what you have to do, like, to get the Thevenin's equivalent circuit, you will disconnect the load from the terminal. Okay, and then have a circuit like this. Okay, here the load resistor is disconnected, and then you will find out the PD, the voltage across the terminal AB, like the terminal from which the load resistor has been taken out. Okay, that voltage will be the Thevenin's voltage, and then from that circuit where the load resistor is absent, okay, on that circuit, from that circuit find out the equivalent resistance. That resistance will be the Thevenin's equivalent resistance. Okay, so you see, in the Thevenin's equivalent circuit, the Thevenin's equivalent resistance R, small r, is connected in series with the load resistor, right? So from the Thevenin's voltage, the load resistor will take up its PD, its voltage, right? So that's why I said the Thevenin's voltage is basically the voltage that is available for the load resistor to take out. That's it. Okay, now we got the Thevenin's voltage there, we got the Thevenin's equivalent resistance, fine. So now there's a very confusing question. Most students get confused in this part. The question is, why the resistance, internal resistance, that is the Thevenin's equivalent resistance, the small r you can see here, it's connected in series with the load resistor. Okay, I'll explain that question, but before that I would say, when I said Thevenin's voltage, I said the Thevenin's voltage tells you what much voltage will be available for the load resistor to take up when you connect the load resistor to the original circuit. Okay, so at the beginning I said the Thevenin's voltage is the voltage across the load resistor, but it's not true. It's not correct. Okay, the correct thing is the Thevenin's voltage tells you how much voltage will be available for the load resistor to take up from the original circuit. Now come to the question. The question is why the resistance, the internal resistance R, is connected in series with the load resistor. Because we got the PD across the terminal AB, which was supposed to be just across the load resistor, not the internal resistance, because we are calculating across the terminal AB. But the fact is the Thevenin's voltage, it gives you the terminal PD of what? Terminal PD of the original circuit when the load resistor is removed. So when you say terminal PD, you can relate something with electrical quantities. There's a formula that is I'll show you from the Kirchhoff's law from the previous part. EMF, total EMF is equals to sum of the PDs, V term plus V lost. Can you remember this equation from A levels EMF and internal resistance chapter? Okay, so here we are getting the terminal PD, V term across the terminal AB. So VAB is basically this V terminal. Okay, so which means the Thevenin's voltage is giving us the terminal PD for the original circuit when the load resistor is removed. So if you make V term the subject, you get EMF minus V lost. That means the Thevenin's voltage, it gives you the maximum effective voltage that the circuit can provide to its components. The maximum effective voltage that the circuit can provide to its components, because the V lost, it's due to the internal resistor IR, the voltage lost in the internal resistor. Okay, so that's why it's giving the terminal PD. That means the Thevenin's voltage, it will be used up by both the resistors and the load resistor except the internal resistor of the original circuit. Okay, this is the Thevenin's theorem. Done. Next is the Norton's theorem. Okay, so I'll explain the both theorems first, and then we will go over some examples. 3 examples I have picked up for this video tutorial. Okay, so we have covered Thevenin's theorem. Now Norton's theorem. So Thevenin's theorem tells you the voltage that will be available for the load resistor when you connect it to the original circuit. So voltage is cleared. Now remaining is the current. Norton's theorem will tell you the current, like how much current will the load resistor get from the original circuit when it will be connected there. Okay, so what's the Norton's theorem says? Any circuit driving a load resistance RL can be replaced by a single current generator IS in parallel with a single resistor. Okay, now the question here, why in the Norton's theorem the current source is in parallel with the internal resistance R, small r, and the load resistor? Why is it in parallel? Why not in series? The reason is, we know that we learned from the Kirchhoff's laws that in parallel circuit the currents get divided according to the resistors, right? So in the original circuit, if we want to find out how much current will be available for the load resistor, then we need to check how much current will be flowing through the load resistor specifically. Individually, how much current will the load resistor get? So in that case, if you connect the internal resistance R, the equivalent resistance R, and the load resistor in series, then how come you get the current specifically flowing through the load resistor? Because in a series circuit, current is constant. So you are not supposed to get the current if you connect both the internal resistance R and the load resistor in series. So that's why you have to connect them in parallel, and that's what exactly the Norton's theorem does. Okay? The resistors are connected in parallel so that you can find the current flowing through the load resistor specifically. Okay? The value of Is is the current that would flow between the output terminals of the circuit if the load resistor were replaced by a short circuit. Have a look. This is the Thevenin's equivalent circuit, right? So in this Thevenin's equivalent circuit, if you short circuit the load resistor, short circuit means like instead of the component, load resistor is a component. Instead of the component, you put non-resistive wire there, just a wire there without any component. So that would be just a circuit, complete circuit with no load resistor in the Thevenin's equivalent circuit. So this is the Thevenin's equivalent circuit. I will draw it fast. This is the Thevenin's equivalent circuit, and we short circuited. Look, it's a straight line with no components. Okay, connected in series with the internal resistance R. Okay, which is this internal resistance R is basically RTH. Okay, the Thevenin's equivalent resistor. Then the current that would flow through this circuit will be the current source Is. The current source Is, you see here, this is E over R. I equals to V over R, the Ohm's law. As I said, the reason why I explained Ohm's law, the Kirchhoff's law, and the potential divider circuit rule at the beginning, because all will be required here. That's how you should relate. As you relate, you can understand better. Okay? So Is equals to what? I equals to V over R, right? So E over, the only resistor here is the RTH. So this is the current through the what? This is the current through the Norton's equivalent circuit. The current generator, they say it there. Is it current generator? Yes, Is. Done. Okay? So the easiest way, I have explained the Norton's theorem, why it is in parallel. You got the answer. And what does the last point say? The value of R, the internal resistance, is the same as the Thevenin's equivalent resistance for the circuit. It's the same. This is RTH. Okay? Okay. So the most important thing is to understand the Thevenin's equivalent circuit. If you can understand the Thevenin's equivalent circuit, then you can easily convert the Thevenin's equivalent circuit to the Norton's, just connecting the load resistor and the internal resistance in parallel with the current source and finding the current using this formula. That's it. Okay? So we have covered the Thevenin's theorem and the Norton's theorem. And another thing I must mention, that the Thevenin's theorem and the Norton's theorem are just the way we represent the circuits in a different manner or different pattern. Okay? It's not like as we are finding the equivalent circuit, like the Thevenin's equivalent circuit or the Norton's equivalent circuit, the magnitude of the current through the load resistor or the voltage through the load resistor will get changed. The voltage and the current through the load resistor will remain exactly same as it would be in the original circuit. Okay, it's just the way we represent will be different, but the magnitude, the current, the voltage, the resistance, everything will be as it is. Okay, so that's why it's very effective. Like, rather than analyzing a very complex circuit, we have to analyze a very simple circuit with two resistors and a power supply. It's very easier, it's very simpler, right? So that's what exactly you need to understand, like the significance for the Nortons and the Thevenins circuit, like theorems. Okay, so I'll show you in three examples. Like in the next three examples, we will check the current and voltage through each of the resistors in the original circuit and then relate it with the Thevenin's equivalent circuit and also the Norton's equivalent circuit. Okay? Okay, so right at first, I picked up a simple example. That's example 2.6. So that's a circuit you can see. So the circuit has EMF source 10 volt, the resistance R1 50 ohm, R2 is 150 ohm, R3 is 100 ohm. You can see on the diagram. And resistor, the load resistor R, it's 200 ohms. Okay, so the question is asking to find the Thevenin's equivalent circuit and the current in the load resistor R. So we will find the Thevenin's equivalent circuit using the Thevenin's theorem, and we will find the current in the load using the Norton's. So both, I will use both the theorems, and also I'll show you by finding the current and the PD across each of the resistors R1, R2, R3 and R. I will find current and voltage across each of the resistors from this original circuit and then show that this is remaining exactly the same in the Thevenin's equivalent circuit and the Norton's equivalent circuit. Let's start. At first, the original circuit. So in the original circuit, let's find out the equivalent resistance. The equivalent resistance for the whole circuit at first. So if we want to find the equivalent resistance, we have to check out the nodes, like how the current is getting divided. Okay, so from which way we can start? Okay, let's have a look from that side. Okay, from the right end. Okay, resistor R, it's basically in series with the resistor R2, right? So if you add in series circuit, we know that the resistance gets added up. So R plus R2, because they are in series. So this is 350 ohms. Okay, now as you get into this point, you see this is junction, current will get divided there. Okay, so if current gets divided there, then that means they are in parallel. So this 350 ohm, it's in parallel with the R3. So if this is the case, then if you want to add 1 over R3, so 1 over R3 plus 1 over the series resistance, which is 350, which is R plus R2, I'm writing directly, okay, equals to 1 over RP, the parallel combination. Okay, so just find out RP using these values. 1 over R3 is 100 plus 1 over 350 whole inverse. So how much it would be, like adding parallel resistors, 1 over 100 plus 1 over 350 whole inverse. So that would give you 700 over 9 ohms. Okay, we got the resistance till that part. Okay, now the only remaining resistor is the 50 ohm resistor, which is in series with the combination on the right hand side, right? So 50 plus that much, so total resistance R total, we got the total resistance for the circuit, it is 700 over 9 plus the 50 ohm resistor. So the total resistance we get here 700 over 9 plus 50. So 1150 over 9 ohms. Okay, we got the total resistance. Okay, so we have the EMF. So from that we can easily find out the total current of the circuit. I total. So I total equals to V over R. V is 10 over total resistance is 1150 over 9. That much amps. So you get 10 over 1150 over 9. So that would give you 9 over 115 amps. Okay, we got the total current. Now we will find out the PD across the load resistor, because in the Thevenin's voltage, Thevenin's theorem, all we want to see is how much voltage is available for the load resistor, right? So if we want to find out the PD across the load resistor, then we need to find out the current and voltage across each of the resistors, each of the part of the circuit. So we will do this. Okay, for R1 at first. Okay, I have no space. Okay, no problem, I can extend it. So for R1, PD across R1 is how much? V equals to IR. So V1, R1 has PD V1, R1 V1. So V1 has the current, it's the total current passing through R1 because it's in series, right? So total current is 9 over 15, 115 I times its resistance is 50, that much voltage. So let's find out 9 over 115 times 50, that would give you 90 over 23, 90 over 23, that much volt. Okay, so that means the remaining voltage available for this end, okay, for this part, if I circle it for this part, it will be the V remaining. Look, V remaining will be the total voltage is 10 minus 90 over 23 volt. So 10 minus 90 over 23 volt, that would give you 140 over 23 volt. Okay, that's the PD across the resistor R3, right? Okay, how is it the PD across the resistor R3? Because the resistor R2 and R are in series. As we consider from the left, R2 and R, these two resistors are in series, and R3 is in parallel with R2 and R. How is it parallel? Because if you see R3, it's in a like through a loop. It's through a loop where the current is getting divided. Just simply try to think. If I ask you, is it the same current passing through R3 and R2 and R? No. R3 has a different current. The pathway is different for current through R3, and the pathway through R2 for current is different. So that's why they are in parallel, simply. Okay, so we got the PD across R3 then. The PD across R3, that is V R3, V of R3, this is also 140 over 23, that much volt. Okay, and PD across R2, and that's R, it is same 140 over 23 because they are in parallel. Okay, so using the voltages you can find out the current. So current through R3, I equals to V over R. So 140 over 23 V over the resistance for R3 is 100, so that much amps. So you will get 140 over 23 over 100, which is 7 over 115 amps. Okay, So the remaining current will flow through the next loop, that is the loop of R2 and R3. So you can easily find out R2 and R3. Sorry, it's not R2 and R3, it's R2 and R, the load resistor. So current flowing through R2 and R, it will be the total current minus the current through R3. Total current is basically 9 over 115. So 9 over 115 minus 7 over 115, which means 2 over 115. So now look, 115, sorry, amps. So we got the current that is flowing through the load resistor. So I am writing it specifically, R load, the load resistor, it is 2 over 115. I'll show you it's the exact current that will flow through the load resistor in the Norton's equivalent circuit. So PD across through R load, you can easily find out how. We know the current, V equals to IR. We know the current, so current times its resistance. So 2 over 115 times how much is the resistance for R load? It's basically 200 if I'm not wrong. 200, yes. So that would give you 80 over 23 amps. Sorry, voltage. Volts. We got the current, we got the voltage. These are the most important thing we need. Okay. Now we will go to the Thevenin's equivalent circuit. Okay, I need more space. I'll drag it down. Okay. Now in the Thevenin's circuit, where's the circuit? Okay, here's the circuit. For Thevenin's equivalent circuit, what we will do first, we will put out the load resistor, right? So in Thevenin's circuit, what happens in the Thevenin circuit? Look, this is E1. This is the EMF source. Are there any resistor? No resistor, sorry. Okay, it goes that way, and here we got a resistor R1 if I'm not wrong. Yes, R1. Then it goes up, the parallel resistor, and then we got 150 ohm resistor there. We will take out the load from here. Okay, this is R1, this is R3, and that is R2, right? R3 and R2. So 50, 100, 150, 50, 100, 150 ohm. So we know that Thevenin's voltage is basically the PD across this terminal. This will be the VTH. So EMF is 10 volt, right? Okay, now how can we find the Thevenin's voltage? Okay, so for finding Thevenin's voltage, you have to apply the potential divider circuit equation, potential divider equation. Okay, since the two terminals are open now, there will be no current flowing through R2. Okay, so that means the output voltage will be now across the resistor R3. Okay, so if you just find out the output voltage across the resistor R3, that would be the Thevenin's voltage, just using the potential divider equation. Okay, so V out that is equals to PD across the resistor R3. This is equals to the Thevenin's voltage. This is equals to, what was the equation we got previously? V output, the equation for V out. Okay, V out equals to R2. R2 is the resistor across which the output is taken. This is R2 times the EMF. So R2 times the EMF. So we are taking output across the resistor R3. So we have to multiply EMF with R3. EMF is 10 times R3 is 100 over then the sum of the resistors R1 plus R3. So 100 plus 50, that much volt. Okay, so this is basically 1000 over 150, which is 20 over 3 volt. We got the Thevenin's equivalent voltage. Now the internal resistance, the Thevenin's equivalent resistance, VTH. So VTH is basically the total resistance of the circuit after the load resistor has been taken out. So in that case, how much would be the total resistance for this circuit? Because here load resistor is absent, isn't it? So 50 ohm resistor is in series. So this is 50 plus, as it is 50 plus. Then 50 ohm resistor. Okay, so if you think, wait, it's not 50. Basically, the resistor R2, it has resistance of 150 ohms, right? If you see from the right end of the circuit, of the open circuit, resistor 150 ohm is alone, right? And this EMF source, it has positive end that way, negative end that way. So current will flow positive to the negative end, right? So that means if you short circuit, if you connect this end, okay, not need to connect this end, we have taken out the load resistor from the terminal AB, so keep it as it is. Okay, so 150 ohm resistor, it's basically alone there on the right end. And for resistor R1 and R3, there are two resistors R1 and R3 are basically in parallel. How they are in parallel? Have a look. Look at this junction. This is junction. That's another junction, right? So R1 and R3 are in parallel. So the total resistance for, I'm just finding the total resistance for this circuit without the load resistor. Okay, so after the load resistor has been taken out, R1 and R3, the circuit is incomplete. That's why R1 and R3 are in parallel now. So their total resistance is 1 over 150, 1 over 50 plus 1 over 100 whole inverse, right? So how much that would be? 1 over 50 plus 1 over 100 whole inverse. This is 100 over 3, 100 over 3 ohms. Okay, and then 150 is in series with this whole combination. With this whole combination, it's in series. So 150 plus 100 over 3, that would give you 550 over 3 ohms. That's the Thevenin's equivalent resistance. Sorry, this is RTH. Okay, now I'll draw the Thevenin's equivalent circuit. Okay, I need to move them, drag them down. Okay, these are basically the next examples. Okay, so the circuit, the Thevenin's equivalent circuit, we know that the Thevenin's equivalent circuit, in the Thevenin's equivalent circuit, the source will be the Thevenin's voltage, what we got 20 over 3 volt. Okay, and the resistance, the RTH, will be in series, RTH, which is 550 over 3 ohms. Okay, with the load resistor. Okay, let me draw it perfectly. Okay, the figure will be not so perfect. Okay, just for understanding. So this is R, load. So for our load, the resistance is 200 ohms, right? 200 ohms. Now look, can we find the current? How much is the current flowing through this circuit? Remember, this current, the current we are finding, it's not the Norton's equivalent current. Norton's equivalent current is different. Okay, Norton's equivalent current will be when we short circuit the load resistor. This is Thevenin's equivalent circuit. Thevenin's equivalent circuit. So from that circuit, if you short circuit the load resistor, then the current you would get, that's the Norton's equivalent current. But I need this current, so this current is I equals to V over R, right? So I equals to V over R. V is 20 over 3, and the total resistance is 550 over 3 plus 200, that much amps. So 20 over 3 divided by 550 over 3 plus 200. So how much you would get? 2 over 115 amps. And surprisingly, this current will be flowing through the load resistor, right? The PD across the load resistor, V load, it is V equals to IR. So we got the current, right? So multiply this by the resistance, which is 200, you will get 80 over 23 volt. So this PD, the PD across the load resistor, and the current flowing through the load resistor, it's exactly similar to the PD and current to the load resistor that we found from the original circuit. You see? So the circuit, we are making it simpler, but we are not changing the values of the resistance or voltages or the current. Okay? Now for the same circuit, the Norton's equivalent circuit diagram, if I draw it here, we will solve it here just at the bottom. Okay, this will be the source, Norton's source, which is IS. Okay, so the resistor must be in parallel with the source. Also the load resistor should be parallel. Okay, so now we have to find out IS. IS equals to the Thevenin's voltage, which is E over the load, the Thevenin's resistance. So E is 20 over 3, isn't it? If you short circuit the load resistor, okay, then only the RTH is there. So I equals to V over R. V is 20 over 3 and resistance is 550 over 3, that much amps. So what would we get? 20 over 3 divide 550 over 3. This is 2 over 55 amps. This is the current, Norton's equivalent current. Okay, so we got Norton's equivalent current. This is 2 over 55 amps. Okay, so since the circuit in parallel, okay, so that means the PD across all the components are the same, and we know that the PD will not change, right? We got the PD across the load resistor. This is 80 over 23. That means the PD here will be 80 over 23 volts because it's not changing. This is the PD across the load resistor. Okay, so how much current the load resistor will get? because the current you got there, this is greater than the current through the load resistor. 2 over 115, it's less than 2 over 55, because in Norton circuit the current that you get here, it's basically the total current that will flow through the Thevenin's resistance and the load resistor. So now you can easily find the current that will pass through the load resistor. This is I equals to V over R. We know the V. 80 over 23. V over the resistance is 200. Right? I equals to V over R. So you'll get 80 over 23 divided by 200. Okay? So you get 2 over 115 amps. Okay? We get the same current in the Thevenin's equivalent and also in the Norton's equivalent circuit. So in both the circuit, our main focus is on the load resistor. How much current will be flowing through the load resistor? How much voltage will be across the load resistor? It will be always the same, whatever circuit you consider. Thevenin circuit or Norton circuit, whatever you consider, in all the circuits, the load resistor will have the same voltage, the same current. Okay? Norton's equivalent circuit. So that's the end of the example. Fine. Okay, so let's have a look on the next example. That is example 2.7. So here we got more advanced circuit, a more complex circuit, you can say. So in this circuit, we have to find the current and the voltage across the load resistor. Okay, we will use both the Thevenin's theorem, the Norton's theorem, and also I'll use the original circuit to show how it relates, like as we did for the previous example. Okay, so let's get started. So at first we have to find the total resistance for the circuit, like for the original circuit. Original circuit. Okay, so for the original circuit, if we want to find out the total resistance, have a look. From the right end, the resistors, 10 ohm resistor and the 15 ohm resistor are in parallel. Okay, so their total resistance will be 1 over 10 plus 1 over 15 whole inverse. Okay, so that would give you 1 over 10 plus 1 over 15 then whole inverse, that is 6 ohm. Okay, this 6 ohm resistor, that means this whole combination is in series with the 5 ohm resistor. So 6 plus 5 ohm, we will get 11 ohm. Okay, now at this junction the current is getting divided, right? The current is getting divided between the resistors. 5 ohm resistor, like through this way, and that's the like input, like from where it is entering the junction. Okay, so we got parallel combinations. Okay, so this 11 ohm, that means this whole part now, this 11 ohm is in parallel with the 20 ohm resistor. Okay, so their total resistance will be 1 over 11 plus 1 over 20 whole inverse. Okay, so our total will be Let's find 1 over 11. 1 over 11 plus 1 over 20 whole inverse. This is 220 over 31. So 220 over 31 plus the resistance, 5 ohm resistance in series. So that would give you plus 5, 375 over 31 ohm resistance. That's the total resistance. Okay, from there we can find out the total current. I total, this is I equals to V over R. So 6 over, resistance is 375 over 31, that much amp. So 6 over 375 over 31, that would give you 62 over 125, that much amps. We got the total current in the circuit. Okay, now we will find the current and voltage across each of the sectors one by one. At first, 5 ohm resistor, the one that is on the left, okay, left end of the circuit. So V across the 5 ohm resistor on the left, V equals to IR. So current, total current will flow through that resistor, 62 over 125 times its resistance is a 5 ohm. So 62 over 125 times 5, that would give you 62 over 25 volt. Okay, and total current will be flowing through that resistor because it is in series. Okay, so remaining voltage, V remaining, it is the total voltage, it's how much? 6. So 6 minus 62 over 25, that much volt. So 6 minus 62 over 25, that would give you 88 over 25 over 25, that much volt. That would be the remaining voltage, which will be across. Okay, let me erase that part, these circles. Okay, so which will be across this whole part, from this, starting from this, sorry, 20 ohm resistor will be also there. So from here, excluding the 5 ohm resistor on the left, including all the resistors on the right of the 5 ohm resistor. Okay, so if you see now, the 20 ohm resistor is in parallel with this combination, right? So PD across the 20 ohm resistor, it is the PD we got 88 over 25. Okay, so PD across the 20 ohm resistor, V20, it is equals to 88 over 25 because it is in parallel with the whole right section of the circuit. Okay, now that means the PD across this part is also the same. Okay, so from there we can find the current, like how much current will flow through the 20 ohm resistor. So I20, so we know the voltage, we know the resistance, so we can easily find out the current. I equals to V over R. V is 88 over 25 over resistance is 20. So this is 22 over 125 amps. 125 amps. Okay, so that means the remaining current will flow through the 5 ohm resistor, right? Because if you see here, let me erase this part, the total current is getting divided into two parts. Here the total current enters, like some amount of current flows through 5 ohm resistor, some amount flows through 20 ohm resistor. So we got how much flows through 20 ohm resistor. So current through the 5 ohm resistor, I5, that would be the total current. Total current is basically 62 over 25, 125 minus the current through the 20 ohm resistor, 22 over 125. Okay, that much amps. So 62 over 125 minus 22 over 125, so that would give you 8 over 25. 8 over 125. That much amps. Okay, so we got the current through the resistor, 5 ohm resistor, this one. Okay, so we can now find out the PD, right? V5 equals to V equals to IR. Current is 8 over 125 times the resistance. The resistance is 5. That much volt. Okay, so 8 over 28 over, okay, it's basically 8 over just 25. Let me check again. 62 over 125 minus 22 over 125, that is 8 over 25. Sorry, that's 8 over 25. So 8 over 25 times 5, it is basically 8 over 5. So 8 over 5, that is 3.6 volt. Okay, this is 8 over 5 volt, 1.6 volt, sorry, not 3.6, 1.6 volt. So what I said earlier, this whole part is in parallel with the 20 ohm resistor, right? And PD across the 20 ohm resistor, it is 88 over 25. 88 over 25. That means this whole part has a PD of 88 over 25 volt. And we already got the voltage across the 5 ohm resistor. So we can find out how much PD is across the parallel section. Easy. Okay. So we got the total PD across the 20 ohm resistor. It is 88 over 25. So PD across the parallel section, the parallel V parallel equals to the remaining PD, 88 over 25, 88 over 25, 88 over 25 minus 8 over 5, that much volt. So since they are in parallel, the value for V parallel will be the same for the voltage across the load resistor. So 88 over 25 minus 8 over 5. So this is 48 over 25 volt. 48 over 25. 48 over 25 volt across the load resistor. Okay, so we got V load, we got V, the PD across the load resistor, it is 48 over 25 volt. Now we need the current. Okay, so current I equals to V over R. Okay, so 48 over 25 I over resistance is, for the load resistor it is how much? It is 10 ohm. Okay, 48 over 10, that much amps. So 48 over 25 divide 10, that would give you 24 over 1 25 125 amps. Okay, so the load current, it is 24 over 125. That much ampere. Okay, we got the current, we got the voltage across the load resistor. Okay, now for the Thevenin's equivalent circuit, we need to draw the Thevenin circuit excluding the load resistor, right? So that would be Thevenin's circuit okay, so we need to draw the Thevenin circuit. Okay, so Thevenin's theorem. Using the Thevenin's theorem, we will find the PD across the load resistor. So here you go, the circuit. Okay, how was the circuit? I need to check. Five ohm, 20 ohm, 5, 15, 5, 20, 5, 15. 5, 15, then 5, 20. Okay, and that terminal will be now open, right? Let's say this is A, this is B, so we will get the PD across this terminal will be the VTH. Okay, 5 ohm, this is 15, 5, 15, 5, 20. Yeah, 5, 15, 5, 20, 5, 15, 5, 20, 5, 15. Okay, ohm. Okay, this is the circuit after the load resistor has been taken out. Okay, now we need to find the Thevenin's voltage, right? And then we will draw the Thevenin's equivalent circuit. Okay, now we have to apply the potential divider circuit equation. So using the potential divider circuit equation, the input voltage was 6 volt. Okay, so we will find out how much output voltage will be across the 20 ohm resistor. Okay, this is V out. Why across 20 ohm resistor? Because the PD across 20 ohm resistor will be given to the resistors on the right. That is the 5 ohm resistor you see here. It will get PD from the PD across 20 ohm resistor. The 15 ohm resistor you see here, this one will also get the PD from the 20 ohm resistor. Okay, so potential divider circuit equation, V out equals to the EMF 6 volt times the resistor across which we are considering the output voltage. So this is 20. Is it 20? Not actually, because this PD, it's across this whole left section. So that means it will cover this whole part. That means it has to be not 20. We have to find the total resistance for this section, the circle section. So the total resistance will be 15 and 5. These two are in series because there's no current. No current in this way, right? So 15 plus 5, this is 20. So and now they are in series, sorry, in parallel, because current is getting divided, isn't it? They are getting different current. The current is following different pathway to reach 5 ohm resistor, 15 ohm resistor, and the 20 ohm resistor, right? So 1 over 20 plus 1 over 20 inverse. Total of 15 plus 5, this is 20. Okay, so this is basically 10 ohm in total. 6 times 10 over the sum of the resistors, that is 5 ohm resistor is here, right, plus 10. So 6 times 10, it is 60 over 15, which is 4 volt. Okay, now this 4 volt will be supplied across the 5 ohm resistor, 15 ohm resistor, and the load voltage. Okay, load resistor. So this is 4 volt. Now consider this as the EMF source, like as we did for this one. Okay, so 4 volt is the EMF. Okay, we need to find out the PD. Okay, let me erase this part now. We need to find out the PD across the 15 ohm resistor, that will be the VTH, right? So if we just find out the output voltage across the 15 ohm resistor, we are done. Okay, which will be the VTH. So VTH equals to, what's the EMF? EMF is now 4 volt, right? So 4 times the resistance of the 15 ohm resistor, it is just 15, right? There's nothing parallel to the 15 ohm resistor because load is taken out, isn't it? Over 15 plus 5. So how much you get? 60 over 20, which means 3 volt. We got the Thevenin's voltage, 3 volt. Okay, now draw the circuit. This is 3 volt. Okay, 3 volt. Thevenin's resistance RTH. This is the load resistor R load. Both are in series. Okay, now we need to find out the Thevenin's resistance RTH. Okay, so to find out RTH, it has to be like this, right? Now we have to calculate the Thevenin's resistance. Okay, so how much would be the Thevenin's resistance? Okay, start from the left end. We have 5 ohm resistor there, right? So this 5 ohm resistor, it's in parallel with the 20 ohm resistor. This 5 ohm resistor, it's in parallel with the 20 ohm resistor. Okay, then we will add the resistance of the parallel combination between 5 ohm resistor and the 20 ohm resistor, and then we will add in series with the this 5 ohm resistor in the middle. Okay, so let's find the resistance for the parallel combination. 1 over 5 RTH will be 1 over 5 plus 1 over 20 inverse, which will give you 20 in the denominator. So 4 5, which is 4 volt, sorry, 4 ohms. Let me check it out. 1 over 5 plus 1 over 20, then inverse is 4 ohms. Okay, so 4 plus 5, it's basically 9, right? 4 plus 5, it's 9, and then we have 15 ohm resistor. So this 15 ohm resistor will be in parallel with this 9 volt, because from this combination we got 4 volt. Okay, this 4 volt adds with this 5 volt to give you, sorry, not volt, it's ohm, 9 ohm. Okay, 4 ohm, 9 ohm. So this 9 ohm is in parallel with the 15 ohm resistor. Now the question is why? Because when you connect the load resistor, the current will basically get divided. It's not following the same way. The same current is not flowing through the 15 ohm resistor. Rather, it will flow through the load resistor. That's why they are in parallel. Okay, so 4 plus 5 ohm, that would give you 9 ohm, and then we have to find out the parallel resistance. 1 over 9 plus 1 over 15 whole inverse, that much ohm. That would give you 1 over 9 plus 1 over 15 whole inverse, that is 45 over 8. 45 over 8 ohms. We got the Thevenin's resistance. This is 45 over 8 ohms, and our load, it is basically 10 ohm as per the question, if I'm not wrong. Let me check it again. It's in the previous page. Where's the R load? 10 ohm. Yes, correct. Okay, so now we can find the current, like how much current will flow through the load resistor. I equals to V over R, right? So we need the I to show that it's similar to the what we got from the original circuit, V over R. So 3 over, total resistance is 45 over 8 plus 10, that much amps. So 45 over 8 plus 10, it is 125 over 8. So 3 over 125 over 8, that is 24 over 125 amps. And the PD across the load resistor, V equals to IR. So 24 over 125 times its resistance is 10, that much volt. So multiply by 10, you will get 48 over 25 volt. And this is exactly similar to what we got from the original circuit. 48 over 25 and 24 over 125, exactly similar. Okay, then Norton's equivalent. We need the Norton's equivalent circuit. So source is there, okay, internal resistance has to be in series, that is the RTH, okay, in parallel, sorry, and the load resistor in parallel, R load, okay, they connects together, that's fine. Now we need the current. IS equals to, we have to consider short circuiting the load resistor, right? So IS equals to the E, this is the E, so E over RTH. So 3 over 45 over 28, 45 over 8, sorry, 45 over 8, that much amps. So the current you will get 3 over 45 over 8, that is 8 over 15 amps, 8 over 15 ampere. Okay, and as we know, the load resistor, it must have the same voltage, so the PD is basically 48 over 25 volt. Now we can easily find out the current I through the load resistor. I equals to V over R. So 48 over 25 divided by 10, that is 24 over 125 amps. Same. Done. So that's the end of the second example from Thevenin's and Norton's theorem. Fine.